if, Sarah, this one's for you, you can tell us how to do this one, or you can just give us the answer. It's a little bit of a review of the review that we just did, but it'll catch us up, get us all on the same page. Given that Ka for benzoic acid is 6.28 times 10 to the minus 5, what is the Kb for sodium benzoate, which is the conjugate base of this acid? What do you think, Sarah? Is the answer up there? Or you can tell us how you're doing it as you do it, or I can do it if you tell me how to do it.
Do we need to know Kw to solve this, or is...
We do, but Kw is always the same. Do you remember what it is by chance?
Is it just 1 times 10 to the negative 14th?
That's right. 1 times 10 to the minus 14. That is our Kw. So what are we going to do with that value?
Okay, so you just divide that by 6.28 times 10 to the negative 5th.
Okay, and is that our answer, or is there something else we got to do?
I think that's it.
That's right, that's it. So we took our Kw, and we knew that our Ka times Kb, Ka for any given acid, times Kb for that acid's conjugate base will equal Kw. So 1 times 10 to the minus 14 was our Kw. We divided it by Ka, and then the result was our Kb. Okay, very good. Now, with information from Chapter 16 and Chapter 15, we find ourselves in a situation that we can predict the pH of a lot of new solutions, a lot of different solutions, using an ice table. So, for example, if I'm given the concentration of a weak acid, we can predict the pH. Now, let's do a quick review of how we can predict the pH given the concentration of a strong acid. And this question is for you, Brielle, so help me out here. If I have a concentration of HCl, which is 0.03 molar HCl, what is the pH of this solution? Do you remember how we do that, Brielle?
I think you can use that concentration for the hydrogen concentration. So you would just take negative log of 0.03 and that should give you the pH.
That's correct. That's correct. Now, how did you know that I could just use the acid's concentration as the hydrogen ion concentration?
Because it has the hydrogen ion when it breaks apart, I think.
That's exactly right. But then essentially what you're saying is you knew that this was going to dissociate completely. How did you know this was going to dissociate completely?
Because it's a strong acid.
That's right. So when we get information about the concentration of the strong acid, it's essentially giving us the concentration, information about the concentration of the hydrogen ion. Because single arrow in solution, acids will completely dissociate. Okay, so, and I'll just do that because we don't want to leave it undone. Negative log 0.03, 1.528. So the pH of this solution is 1.528. Okay. Very good. Now, and I'll tell you that we don't yet, well, we haven't done any examples. We do have the tools to do it, but we haven't done any examples. But if I said, what is the pH of a 0.03 molar solution of this acid, HC2H3O2, which is acetic acid. What's the pH of 0.03 molar acetic acid? Okay. Can I take the negative log of this concentration and just have that be the pH? The answer is no, Why not, Jace? Why can't I just take the negative log of the 0.03 here to find the pH?
Is it because it hasn't like dissociated yet, or?
It's because it's a weak acid, right? It's not a strong acid.
Oh, okay.
It's a weak acid. And so it doesn't dissociate completely. So even if I have 0.03 molar of this in solution, that doesn't mean I'm going to have 0.03 molar of the hydrogen ion. Now, if I knew the Ka, the amount of dissociation that does occur, I could answer this question. I could answer this question because I know that the Ka would equal some value. Let's say if it was 1 times 10 to the minus 4. And I know that Ka equals the concentration of the hydrogen ion in this case for that acid times the concentration of the acetate ion over the concentration of the associated material, right? Associated, not dissociated. This is the dissociated material. This is the associated material. Okay? So how would I find their concentrations? I would set up an ice table. I would say, okay, so we're saying that this acid HC2H3O2 dissociates into H plus and C2H3O2 minus. The initial concentration, we were told, is 0.03. There was none of this initially. And then the change, because there's none of this, and this is supposedly in equilibrium, meaning there has to be some, I know that the change is going to decrease some of this and increase these amounts. So I can say minus x here, plus, again, x, meaning our change, some amount. And then the equilibrium concentration, 0.03 minus x, x, 0 plus x, and 0 plus x, x there. Then I can use these equilibrium concentrations and place them into my equilibrium statement here. X over, these are multiplied by each other, 0.03 minus x. That equals 1 times 10 to the minus 4. And then I could solve for x. Okay? I have x squared up here. I have 0.3 minus x times that. It would make two values resulting in a polynomial, basically, that I'd have to use the quadratic equation to solve. But if you remember, it's been a little bit of time, a couple of classes back. But I don't know, Sarah, do you remember how we might simplify this kind of a problem?
Yes, so if your K is really small, I think you can just ignore the X on the bottom. Because it's essentially 0.
That's right.
Or a really small number.
If this is really small, we could get rid of this value here, and then we could solve that problem easily and solve what x is. And once we got a value for x, then we would know that that's the hydrogen ion's concentration at equilibrium. Negative log of that value would be the pH for the system. Okay, so that was the first introduction. Not really. You guys have kind of done this already a little bit, but we'll practice it now. Here it is, 0.1 molar solution of this acid with a Ka of 1.8 times 10 to the minus 5. Okay? So, did you follow that last example, Brielle? How are we going to approach this problem here?
So first we can write out the equation of the dissociation.
Good.
Into our ice table.
Mm-hmm.
And then, so that would just be HC2H3O2, which goes to H plus the C2H3O2 minus.
Great.
We can use our ice table, which the I for the HC2H3O2 will be 0.1, and then the other two will be 0, and then the C for the first will be minus X, and then the other two will be plus.
Now, how did you know that this was minus X here and not plus X?
Because our Ka was very small,
Okay.
I think.
Well, the real reason we knew here was because in the initial concentrations, there's no product yet. And so when this approaches equilibrium, it's going to have to occur by this breaking down into these species. Does that make sense, Brielle?
Okay. Yeah, that makes sense.
All right, so then what's our equilibrium concentrations for these?
So then it'll be 0.1 minus X, and then the other two will just be X and then X.
Great. Let's pass the baton to Jace and see if he can have any ideas about what do we do next. What do we do next, Jace?
Honestly, I'm not completely sure. I know that. Hold on. We're gonna have to combine all of them to make an equation, and then we're gonna solve for x. But I forget how to do that.
Okay. Well, at this point, we have the equilibrium concentrations of the different components. And
So it's just 2x plus 0.01 minus x equals 1.8 times 10 to the negative 5.
that's right, because we have our Ka up here. And our Ka equals 1.8 times 10 to the minus 5. Ka means, for this scenario, that one is the H plus ion times, not plus, C2H3O2 minus over what?
Over the HCO2H3O2.
Very good.
And then, so yeah, it'll be 2x over 0.1 minus x.
Well, not 2x, it'll be x times x, right?
Oh yeah, so x squared.
Over 0.1 minus x, is that what you said?
Yeah.
Very good. Okay, Jace, now how do we solve this?
We're going to multiply each side by 0.1 minus x, and then we'll have x squared equals 0.1 times 1.8 times negative 5. So let me do that real quick.
Well,
0.1.
hold on just a second. Make sure you I think this is what you said, but I'm not positive. We're going to multiply this bottom number here by this, right?
Yeah, and we'll have to distribute that. We'll have to multiply each one of those variables by 0.1.
But
1.8 times 10 to the negative 5.
yeah,
So it'll be 0.1 times 5. So it'll be 1.8 times 10 to the negative 6 minus 1.8 times 10 to the negative 5x equals x squared.
equals x squared. If I move the x squared over here, I can set that all equal to 0, right?
Yeah.
Now, what would be your favorite way for solving that problem, Jace?
Well, yeah, we're gonna have. Is this where we're gonna?
Oops. Let's see. This is the x here. This is an x. Well, this would generally be, if I got to that point, yes, I'd have to use the quadratic formula. However, I'd prefer not to use the quadratic formula because I'm too old. It was a long time ago, and honestly, I don't have it memorized. Now, I do know how to use my computer, my solver. Remember that? We talked about that one day. I can use my solver. I can type it in, and I'm okay doing that. But I don't remember the quadratic equation. However, there's something even easier that we can do. Do you remember what it was, Jace, what we can do? Hey, Sarah, do you want to tell us? What is it that we can do? What's the even easier step here?
So you can just get rid of the minus x on the bottom because Ka is so small.
All right. So because this value is so small compared to this value, 0.1, it's 4 orders of magnitude away from each other, right? So because and it just has to be like 3 orders of magnitude away from each other. That means this shift, x, is going to be so small compared to the 0.1, it's going to be essentially not going to make a dent in it. So I can save myself from having to do all this by just dropping that term right there. And then that leaves me with x squared equals 1.8 times 10 to the minus 5. And then I can just take the square root of both sides and solve for x. So, what do I got here? 1.8 times 10 to the minus 5. Square root I meant. There we go. So 0.004. 0.004. 0.00424. That is what x equals to. How does that help me, Sarah? Why was I after x? What am I doing here?
Okay, so we're trying to find the pH, and if we see x is our h value, so we can just take the negative log of our number, and that will give us the pH.
Okay, very good. So x here was the concentration of the hydrogen ion, which the negative log of that gives us our pH. So if I just go negative log of that answer, 2.37 then is our pH. Okay, very good. So as we scroll through this, we made our ice table. We put in our initial concentrations. We put in the shift that was going to occur. We looked at the equilibrium concentrations. We identified that this one could be simplified to 0.1 so that we wouldn't have to use our quadratic equation. Then it just spit out x squared over 0.1 times or equals 1.8 times 10 to the minus 5. And then we just solved for x and took the negative log of that value. Very good. So we're in a situation now that if you tell me the concentration of an acid, I can tell you the pH if it's a strong acid. And if it's not a strong acid, if I know the Ka, then I can also tell you the pH, right? One more. We're going to do this one as well. This one, actually, I'm going to give you guys about 3 minutes to solve it. And you might say, oh, that's not enough time. But there's a very familiar pattern, right? You're going to end up with a statement just very similar to this. X squared over 0.1 times equals 1.8 times 10 to the minus 5 for this problem. But we're going to determine the pH of a 0.1 molar solution of this HCN. Okay? So, why don't you guys all take a stab at it, and then we'll come back in just about 3 minutes, and we'll see what we got. Okay? All right, did you get it? Why don't you tell us what you got, Jace? Sarah, are you there?
Yeah, I'm here.
Did you get an answer?
Yes, I got 5.1.
5.1. So, did you set up the ice table like this and think about it, or did you just write down x squared over 0.1 equaling 6.2 times 10 to the minus 10?
I set up the ice table, but
Excellent.
I guess I could have just...
No, that's fine. That's absolutely fine. But it does become apparent, the trend, relatively quickly. And then after you got X, you just take the negative log of that because that is our concentration of our hydrogen ion, and that gives us our 5.1. Is that what you said, Sarah?
Yep.
Fabulous. Okay. We can do the same thing for basic solutions. So if I have a 0.1 molar solution of this material, and I'm told given the Kb for this material, right? Now, I might look at N2H4 and say, I don't know anything about that chemical. How am I going to know what its pH is? But they'll have to provide me some information. And when they give me information like the Kb, then I'll say, oh, if I know that there's a Kb, that means that this chemical, N2H4, behaves apparently like what? What is the Kb telling us, Brielle?
The conjugate base.
Yeah, it's behaving, well, it's telling us that this material behaves like a base. And when it behaves like a base, that means it interacts with water and forms the hydroxide ion. That's what's basic about the solution when you put it into water. And what would be left? What else would be here, Brielle?
The hydrogen ion.
Well, the hydrogen ion on this thing, right?
Mm-hmm.
So what would it be? N2,
H5.
5, and then a
And
positive charge?
Mhm.
All right. Excellent. So we could do the same thing with our ice table. Initial concentration is 0.1. Initial concentration zeros. Change, minus X again. Plus X, plus X. Water is a liquid, so it's not in the equilibrium statement, so I don't have to worry about it. 0.1 minus X, X, X. The Kb for this is given, and that Kb equals hydroxide ion concentration times the N2H5 ion concentration all over the N2H4 material, right? Which will equal, according to our ice table again, X squared over 0.1 minus X, but because the Kb is very small compared to the minus X, I'm just going to be able to drop that minus X. This is going to be equal to my Kb, 1.7 times 10 to the minus 6. And then I can solve for X. All right, so let's fast forward to that point where we've solved for X. And what do you think we do next, Sarah? Once I've solved for X, what am I going to do to get the answer the question?
I think we take the negative log of that.
Okay. Negative log of 4.12 times 10 to the minus 4. All right. Is that the answer then, Sarah? Let's think about this here. This is this supposed to be a base or is it supposed to be an acid, N2H4?
So it's supposed to be base.
Why did we get a pH of 3.38? Isn't that acidic?
Yes.
Or I don't know, is 3.38 not the pH?
So
Is
I
X
don't know.
is X the hydrogen ion concentration here?
No, it is not.
It's not, is it? It's the hydroxide ion concentration. So what is this? This 3.385? Is that the pH?
Is that the POH?
That's right. It's the POH. So if I do 14 minus our value there, whoops, try again. 14 minus our value, that gives us our pH. So the POH was 3.38 and the pH is 10.62. Okay, just a slight wrinkle in there. Why don't you guys finish up this one here? What is the pH of a 0.1 molar solution of ammonia? Okay, I'll give you just a little bit of time. I think you guys are cotton on to the trend of things here. And then, Jace, are you going to be able to tell us the answer to this one? Maybe you can help us, Brielle, when you get it. Did you get it, Brielle?
Yeah, I got the POH to be 11.13.
The pH, you mean, to be 11.13.
Oh, yeah, I meant the pH, sorry.
Very good. 11.13. Excellent. So again, our X, when we're identifying, solving for X in scenarios where we've been given a base, is not the hydrogen ion concentration, it's the hydroxide ion. So we just have one extra step. We take the negative log of it, and then 14 minus that value will give us the pH. Okay. What's the pH of 0.3 molar solution of phenol, an ingredient in some older mouthwashes? Okay. This one, Sarah. What is the general form of this kind of a reaction? What are we seeing here? I mean, if you do all the ice table, you end up with the answer, which is not bad. It's a lot of fun. It's a lot of fun to do those ice tables and follow through. However, we get pretty good at it. We know that we're going to get what? What is the relationship that we're going to get after our ice table?
So it should be x squared over 0.3
0.3 being equal to what?
equals 1.3 times 10 to the negative 10.
Very good. So 1.3 times 10 to the minus 10 times 0.3, and then we take the square root of that value. Oh, what did I do? Oh, I times it by negative 3. Let's try again. 1.3 times 10 to the minus 10 times 0.3, 3.9 times 10 to the minus 11. Whoops. Square root of that value there. 6.2 times 10 to the minus 6. That's not one of our answers. What did I do, Sarah?
We still need to take the negative log of...
Ah, yes, that's right. The negative log of that hydrogen ion concentration. So 5.2. Oh, there it is. Good. Praise the day. All right. Very good. So we find ourselves now with all the tools necessary to know the pH of a solution of any strong acid, to know the pH of the solution of any weak acid, as long as we're given the Ka, to know the solution of any weak base, as long as we're given the Kb, and one that we didn't review this time, but we did before, is the identifying the pH of a solution of strong base. Strong base. When you do the strong base, then the concentration of the base should tell you the concentration of the hydroxide ion, right? Now, sometimes we want to answer information about percent ionization. The K value essentially has the percent ionization kind of hidden in there, but sometimes people want to know this because it kind of helps them think about it in terms of an easier way of thinking, right? 100%, how many of those 100 molecules at any one given time would be dissociated, right? So let's do it. Let's determine the percent ionization of a 0.2 molar solution of HC2H3O2. Okay, same thing. We got a Ka, we need a Ka, we need our ice table, initial concentration, change, equilibrium concentrations. All right, we're in the same spot now. And we need to find out what X is, so we put our equilibrium concentrations in the shape of our equilibrium expression, concentration of the acid times the concentration of the dissociated ion over the concentration of our acid to start with, being equal to the equilibrium constant will allow us to solve for X. And now when we get X, 1.9 times 10 to the minus 3, we haven't been asked what the pH is. We've just been asked what the percent ionization is. So we don't take the negative log of this value. We just find out what percent of our initial stuff, 0.2, actually ionized. So we take this 1.9 times 10 to the minus 3, and we divide it by our 0.2, right, times 100, and that will be our percent ionization. And the answer here is 0.95. So one more time, I solve for X. That tells us the percent of this C2H3O2, right? So I can take that amount, 1.9 times 10 to the minus 3, and I can divide by the amount that I started with, 0.2, times 100, and that'll be my percent ionization of 0.95%. Okay? So another thing that, another parameter, another tidbit of information that people are generally interested in. So we're going to do the same thing now, solve for percent ionization for a 0.1 molar solution of the same material. So remember this number, 0.95%, and we're going to solve for what the percent ionization of a 0.1 molar solution of this material is. Okay? You think you can do it, Brielle?
I think so.
All right. Do you want to do it, walk through it, or do you want to do it yourself and then tell us the answer?
I can do it either way. Does it have a K?
Oops. Yeah,
value?
there it is. There it is. Very good.
Okay. So basically, it's going to be the same equation that we've written out. So if you're okay with them, you don't necessarily need to write an ice table.
Yeah, absolutely.
So we can just do 1.8 times 10 to the negative 5 equals x squared over 0.1. And that will become, take the square root of this. And then our x will become 0.00134.
All right.
And divide that by 0.1. And then times that number.
Okay, very good. 1.34%. Okay, excellent. Now, let's have a little conversation really quick about this 1.3% compared to this 0.95%. 0.95%. So I'll write that data down here so we don't have to go back and forth between the slides. If I have 0.2 molar of my acid, then I get 0.95% ionization. So this is the acid's concentration, and this is the percent ionization. If I have 0.1 molar acid concentration, I got, what was it? 1.3% ionization. So what's going on there? I thought that if we had more, well, we should include one more here, the actual X value, or which is equal to the concentration of our C2H3O2 minus. Okay, so for our 1.3, the X value was 1.34 times 10 to the minus 3. And for our 0.95%, or our 0.2 molar concentration, the X value was 1.9 times 10 to the minus 3. Okay. Now, what's interesting here is if we're asked which one results in more dissociated acid, this one results in more dissociated acid, but it has a lower percentage in terms of how of the per 100 acid molecules that are actually dissociated, but it has more that's dissociated because there was more to start with, so you get more acid dissociated, right? Let's also translate this X value into pH for these two different concentrations. So if I have 1.34 times 10 to the minus, well, 1.9, let's do that one first. 1.9 times 10 to the minus 3, and then I take the negative log of that value. That's 2.72. Okay. Whereas our other one here, 1.34 times 10 to the minus 3, negative log of that, oh, what did I do? 2.87. So lower pH, more acid in solution, but a lower percentage of ionization. Higher pH, less acid, but more dissociation. Okay? So what's going on here? Well, what's happening is, because I have more acid in this scenario up here, right, which results in a lower pH, more acid, again, just the generic acid dissociation so we can kind of think about this, more hydrogen ion, and more A minus, because that's where the hydrogen ion came from, the dissociation. Then we have more of a driving force to go back towards the associated form. So as more of acid is present, then less, a lower percentage of the material will actually be dissociated. Okay, very good. So, percent ionization of this one, we already did that. Let's see, here we are. And we can skip those ones as well. All right, let's see if we can get this, though. Now, pH of a 0.05 molar solution of an acidic drug, HD, that's our nice drug. It's an acid. It's 3.5. What's the value of Ka for the drug? Sarah, do you want to help me go through this one? What would you do for this one? It's new, so if you don't know, you can just say, I don't know, but you can also say, I don't know, but I think I might try something like this, right?
Okay. Well, I don't know, but I think I would find the concentration of H by taking 3.5, or no, 10 to the negative 3.5.
10 to the negative 3.5?
Yes.
And that would tell us the concentration of the hydrogen ion, 10 to the negative 3.5. Okay. Uh, 10, let's see. There we go. So 3.16 times 10 to the minus 4. And that'll give us what?
That's the concentration of H.
Okay, good.
And that's about as far as I can guess.
All right. Well, then let's just kind of fiddle around with some ice table business, right? If we wanted to make an ice table for HD, what would it look like?
All right, so that would dissociate to H plus D minus,
Mm-hmm.
and I guess we have 0.5 for the initial HD, then we'd have 0, and it would be minus X, and then plus X, plus X. So that gives us our, I guess we just know that Ka equals X squared over 0.5.
Okay. So all we really need is X if we want to get the Ka here, right?
Yeah.
Now, does any of this business that we've done up here relate to our X?
Let's see. I'm not sure.
Well, we
Would
said,
that be, yeah, is that the final concentration?
yeah,
Okay.
that's the final concentration of the hydrogen ion, right? 3.16 times 10 to the minus 4. Now, what about this one over here? And does that help us with this at all? Why is it that those X's are the same? As it says they're both X. Are they really both this?
I guess they are.
They are,
Maybe.
but why is it? How is that possible?
Is it because when HD dissociates, it has to dissociate in equal parts?
That's right. So for every H plus you get the same amount of D minus. Okay, very good. So basically, 3.16 times 10 to the minus 4 squared over 0.5 will equal our Ka. Is that true? So there's our X squared divided by 0.5. So I'm looking at 2 times 10 to the minus 7. Did I finish that up right, Sarah? Does that make sense?
I think so.
Did you understand that last part, do you think?
Yeah.
Okay. Great. Excellent. So 2 times 10 to the minus 7 is our answer. Again, we were given information about not the Ka. We weren't given the Ka, but because we were given the pH, we could identify the hydrogen ion concentration, and that would be the X, the equilibrium concentration of hydrogen ion and the equilibrium concentration of our dissociated ion from the acid initially And so then this 0.5 minus x could be simplified to 0.5. All right. Awesome. Such wonderful powers that we're gaining every day. Okay. I think this is a good place to stop because this slide here just gives us a review of what we do when we have strong acid, what we do when we have strong base, what we do when we have weak acid, what we do when we have weak base, and then what we do if we want to find the Ka or the Kb given either any other sort bit of information. Okay, so that's where we'll stop. If anybody has any questions, you can hang out and ask them. Otherwise, we'll meet again on Friday, correct? And we should be able to get through the rest of this chapter. Okay. Thank you, guys. See you later.